Hello, everyone. Good morning, or good afternoon, or good evening, according to your time zone. My name is Rishith Meethal. I'm a researcher at Technical University of Munich, Germany, and Siemens Technology. Today, I'm talking about generalized physics-informed machine learning for numerically solved transient physical systems. This is the agenda prepared for today. We will start with the motivation behind why such a physics guided machine learning model is needed, and then we go into the introduction part where I will take you through the journey of how we came up with such a PGML model. Then we go deeper into the model and its algorithm. After that, we go into some results and discussions where we discuss uh, two transient problems from structural dynamics, single degree of freedom system and multiple degree of freedom system. Then we will conclude our talk with a summary and future work. Yeah, we all know that physical systems of engineering importance are normally represented by partial differential equations, and they are conventionally solved using numerical methods. Numerical methods have matured over years, and they need expert knowledge. Once you make a model, they are computationally expensive when you are considering such a simulation like a 3D wind turbine simulation, and such simulations are not possible in real time. Even though it is not possible in real time, it is okay because most of the numerical methods have matured over years and they are robust and computationally efficient for most of our engineering applications. But when it comes to applications such as digital twin, where we have a digital representation of a physical machine running, you take some sensor measured values and run some simulation to understand whether the machine is going to fail or not. You need to run simulations in real time. Or if we have some applications where we run large number of simulations, for example, uncertainty quantifications or optimizations, where we change the input parameters and run large number of simulations, we need faster simulation. So in those cases, numerical methods are not a option. So people have come up with the surrogate modeling methods. For example, they come up with reduced order models or Gaussian process-based models. But because of its success in the other fields, machine learning-based surrogate models are getting its attention nowadays. So our model is also a machine learning-based surrogate model, combining numerical methods and neural networks. So let's consider how people were approaching the physical problems using conventional machine learning approach. So they were following the conventional ML approach and ML pipeline where they create a lot of data and use, for example, in the neural network, they use mean square error and optimize the neural network to approximate the function between x and y. But what happened is that when it comes to physical problems, we have the lack of training data, and even after we train, the model may not be physics conforming, especially if we are using the model in the untrained region, we get unphysical results. Because of which informed machine learning.
May I ask a question? I'm just curious as
Yeah.
to why you say there's a lack of physical data. I assume in a scenario where you know enough about the physics and underlying equations, it's so you have you have a lot of data, right? So that seems a bit counterintuitive to me. Would you mind expanding on that?
I can explain because, as I said in the first slide, if we are running a lot of, if you are running a 3D simulation, creating a lot of training data itself is a tedious task. So
I see.
It is better to have less data and get a surrogate model, right?
I see. So you're saying because of the simulation time, it's nice to work
Yes.
with Spark. Okay, fair enough. Yeah.
Yeah. Fine. Okay, that is how the informed machine learning approach has come into the picture, where we integrate the prior knowledge into the machine learning pipeline, either in terms of data or in the algorithm or in the hypothesis parts. So there are large variety of ways by which prior knowledge can be integrated into the machine learning pipeline. There is this informed machine learning a taxonomy paper from Rodan and Laura where they explained possible scenarios. For example, if we are considering engineering applications, our source of prior knowledge comes from natural science, and normally we represent it in the form of differential equations, and we try to integrate it into the machine learning pipeline in the learning algorithm, for example, in the loss function. So this is the kind of approach we have been following in the informed machine learning. But when we consider this, there are like two drawbacks or two improvements we can make in this, because most of the algorithms of that type are not really generalizable. For example, if I consider this machine learning pipeline where I am embedding the equation in the loss function. For example, I have two equations here. First one is a stress equation, and another one is the convection diffusion equation on temperature. One need to reformulate the loss function every time we change the physical equation. Or if we were using different blocks for different parts of the equation, that time also we need to redesign our machine learning pipeline. So one can say that it is not really generalizable. So it is good to have a generalizable approach. Another thing we can consider is like most of the algorithms are discarding the developments we made in the classical numerical methods. We know that it has matured over the years and it is meeting the requirements for the practical needs. So if we can combine these two methods, it is always good to have such combined methods. So that is where we are introducing this physics guided machine learning model. So it's an algorithm for transient problems. What we are doing is we are learning a neural network for transient problems using some initial time step data from the transient simulation, and we try to predict the rest of the simulation. So if we consider the first half, the training of the neural network, for every time step, we know that there is some input data which depends on your system and numerical method parameters. So at every time step, we can construct the stiffness matrix and force vector, like when we are considering a finite element method formulation. And at the same time, we can give the input parameters to the neural network and it can do a prediction. And from these three values, like the stiffness matrices and the prediction, we can calculate the residual, like the discretized residual for this particular time step. And we can backpropagate this residual on the neural network to learn the neural network parameters. So this way, we can embed the physics into the learning process. And once we have a trained neural network, we can deploy it for predicting the rest of the simulation. Little more into the loss function formulation. As I said in the previous slide, we get the matrices from numerical methods. Like if we are using finite element method, we can get dynamic stiffness matrix and force vector for each time step. And we get a prediction from neural network for the unknown variable x. And we can calculate the residual of the equation for that time step, like a kx minus f. And then we can use it as the loss function of the neural network. If we were using a conventional neural network, we would be solving this kx minus f using linear solvers, and then comparing this solved solution with the predicted using a mean square error or some other kind of error function. So in this case, this is the loss function we formulated, where t is the number of time steps we use for the training, and n is the number of unknown degree of freedom at each time step. Little more information on how we can use such a loss function. We know that, okay, in neural network, the output layer or output y is connected to your input through a nonlinear function consisting of activation functions and learnable parameters, weights, and biases. And once we have the prediction y, we compare it with the actual y and make an optimization problem, and we try to reduce such an error term or loss term by adjusting the learnable parameters using our update rule, where we need to calculate the derivative of our loss term with respect to our learnable parameter. So for calculating this, we normally use the chain rule, where the derivative of loss with respect to any learnable parameters is a combination of derivative of loss with respect to the output of the neural network and times the derivative of output with respect to the learnable parameters. In this, the first term is completely depending on which loss function you are using, and the second term is completely depending on the architecture of the neural network. So even if you change the loss function, this term does not change. It is completely depending on the architecture of the neural network. So if you are changing a loss function, you need to calculate this term. So for example, for mean square error, we get this gradient of loss with respect to output as this. So in our case, we are using the residual of the equation as the loss function. So when we formulate or calculate the derivative of our loss with respect to output, we get it as residual times the stiffness matrix divided by the loss. So this is the loss function we used for training our neural network. And now let us consider a couple of examples from the structural dynamics we solved using this PGML model. First one, we will consider a single degree of freedom example. Normally, a single degree of freedom example is used to represent any simple vibrating mass which is connected to a spring and a damper. It is represented by second order differential equation in single variable, where x is the response or displacement of the system and f is the force acting on the system. On the right hand side, you can see the response of the system calculated using numerical time integration scheme. On the bottom, you can see the zoomed in response. Here, you can observe that all three variables like displacement, velocity, and acceleration are in different scales. So in the numerical methods, we formulated the system such a way that we solve all three variables together. So we'll be solving a 3x3 metric system. And what we did is we trained our PGML model using the first 5-second data and tried to predict the rest of the simulation. Here the test results are plotted. You can see for all three variables like displacement, velocity, and acceleration, the PGML model is able to predict the results quite accurately, and the absolute error is really low. And here, as I said earlier, we have used a numeric time integration scheme as the reference solution. To see if the error are really low, we plotted the relative error for each variable. You can see that the error distribution are concentrated around 0, and the mean of the error, relative error is quite low. Now we attempted the same algorithm for a multi-degree of freedom system. So in this case, we have tried actual practical case where we model a high-rise building as a multi-degree of freedom system. Normally, high-rise building under a wind load are analyzed using multi-degree of freedom system. So that means that we use lumped mass approximation of the high-rise building, where each mass have 2 degrees of freedom, like x direction and y direction displacement. So compared to a single degree of freedom system, the difference is that here the M, C, K, F are matrices like mass matrix and stiffness and damping matrices and force vectors. So we tested it on a 20 degree of freedom system, and on the right hand side you can see the response of the system over time for some of the selected degree of freedoms. In the plot, you can observe that each degree of freedom behaves completely different from each other, and they are also in different scale and frequencies. So we trained our LSTM neural network for this data, again using the first 5 seconds, and tested it on the next 5 seconds. So here we plotted some of the results. Again, similar to the SRF system, our model is able to predict the reference solution quite accurately, and the absolute error is really low. In this case, we were using generalized alpha time integration scheme. This also shows that okay, our method is applicable in any different numerical methods. Now we wanted to test the robustness of the model, so we tried to predict it for then 5 to 30 seconds. And in this case also, it can be seen that okay, our model is able to predict it quite well. So with this, I reach to the final slide conclusion. So we have introduced a generalized physics guided machine learning workflow for training transient simulations. And this method or this model can be easily adapted to different physics and numerical methods. In comparison to conventional machine learning approach, it is more physics confirming. And when we consider any practical example cases, such a trained model can be deployed in a real system, and the signals from real system can be compared for any prediction anomalies. Even though the algorithm is promising, we need more work to take it to a real application level. For that, we need to consider complex input forces, which represent the real application cases, and we also need to consider other variables which varies over time. And another problem with the present approach is that the error gets accumulated when we do recursive prediction. So we need mechanisms to correct those errors also. Yeah, with this, I end the presentation and I am open for questions and discussions.